Yeah, this is Dr. S. Venkateswarlu, working as Professor of EC at IARE, Hyderabad. Yeah, today we'll discussing about the discrete Fourier transform. So here's the discrete Fourier transform is the transform of finite duration sequence. The sequence before entering this DFT, we know that DTS and CTS with reference to that CTS. CTS, you have to remember that CTS and DTS, discrete time signal. Okay. Yeah, DFS, discrete Fourier transform, corresponds to samples equal spaced in the frequency of the discrete time Fourier transform of the signal. Okay. Here, the DF is the sequence rather than a function of the continuous variable omega. Here, the derivation and interpretation of discrete Fourier transform is based on relationship between periodic sequence and finite length sequence. So before entering that, where DTS, discrete time signal, is equal, what the equivalent of the DTS, discrete time signal, is equivalent to frequency domain. Here it is also coming from that Fourier transform. Okay, Fourier transform. So for this, from this, x into e power j omega. Okay, after that we will expect that what you call x of k, where x of k is nothing but discrete Fourier transform. Okay, if it is Fourier transform, that Fourier transform sampled with a frequency domain, it is followed by x of k, where x of k is the discrete time signal. Is so in Fourier transform, in terms of this x into what you call frequency domain, x into e power j omega with the discrete Fourier transform. Okay, it is the powerful tool. So how it is the powerful tool? We have to distinguish that Fourier series, what you call Fourier transform versus what you call discrete Fourier transform. Okay, here if it is non-periodic, here it is the derivation and derivation interpretation of the discrete Fourier transform is based on relationship between periodic sequence and finite length sequence. It is also followed by a non-periodic. If it is non-periodic discrete time signal, it is followed by x of n. So observe that all frequency response of this, where x into e power j omega. Okay, with this, that x into e power j omega is equal to what you call x of omega. Okay, this is equal to x of omega is equal to what you call the summation where n is equal to minus infinity to plus infinity. Okay, where x of n into the what you call the fiddle factor, x of n into e power minus j omega n. It is followed by equation 1. So with reference this equation, the periodic fundamental range is, you have to observe the fundamental what you call periodic. If you are considering this periodic sequence or periodic, you have to follow that a fundamental frequency range. The fundamental frequency range is 0 less than what you call less than omega less than 2 pi. Like this, we have to follow that fundamental frequency. Okay. So next here, so with this the Fourier series representation of the periodic sequence corresponds to the discrete time Fourier transform of the finite length sequence. Using this all sequence, okay, representation of periodic sequence the discrete Fourier series, how it is appeared. Given a periodic sequence, it is followed by what you call x of n with period n, so that x approximately n is equal to x approximately of n plus r into n. So like this, we will ready to observe the representation of the periodic sequence, the discrete Fourier series. The Fourier series representation can be written as x of n approximately equal to 1 by capital N, the summation x approximately k into e power j into what you call 2 pi by n into k. It is nothing but it's a twiddle factor. Okay, so the Fourier series representation of the continuous time periodic signal require infinitely many complex exponentials. What are the exponential components? For a discrete time periodic signal, so here e power j 2 pi by capital N of k plus m n into n is also equal to that twiddle factor e power j 2 pi by capital N kn into e power j 2 pi mn. So here that k value we have to substitute, where the k value where k equal to 0, 1, 2 and 3, 4 and so on up to it is all depending upon what you call capital N value. Okay, so like this the Fourier series representation of the continuous time periodic signal require infinitely many complex exponentials. For a discrete time period signal like this, and it is also equal to that e power j 2 pi by capital N into k. The k value ready to substitute, where k equal to 0, 1, 2, 3, 4 and so on, capital N minus 1. Okay, next representation of the periodic sequence, the discrete Fourier series, it is followed by e power j 2 pi by capital N of k plus mn power n is equal to e power j 2 pi by capital N into kn. It is nothing but a twiddle factor with the e power j 2 pi mn. Okay, so overall it is equal to e power, after simplifying this, e power j 2 pi by capital N into kn, k value ready to substitute according to the n capital N is decided. For Fourier series representation of approximately x of n, with this where x of n is equal to 1 by n into summation k into n minus 1 x of k e power j 2 pi by n into what you call 2 pi by capital N by n into k and n. So that k value you have to substitute initially, where 0, 1, 2, 3 up to according to capital N there is a deciding factor where n is equal to minus 1. Okay, due to this periodicity, we only need the n complex exponential. For that, Fourier series representation of x of n. Okay, like this, it is also given to this, right? We observe that where x of n is equal to 1 by n into summation k equal to 0 to n minus 1 x of k e power j 2 pi by n into kn. So the Fourier series representation of periodic sequence x approximation of n with this discrete Fourier series pair is required. The discrete Fourier series pair, the Fourier series, we know that one x of n is equal to where this value, okay, or we have seen that where x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 x of k. Here that x of k, where x of k is your d of t, where this is inverse discrete Fourier transform. Okay, here that is product this e power j 2 pi by capital N into kn. To obtain the Fourier series coefficients, we multiply both sides by e power minus j 2 pi by n by into Rn. Okay, so for 0 less than or equal to n less than or equal to n minus 1, and then sum both the sides, we obtain what you call the summation n is equal to 0 to n minus 1 x of n into e power minus j 2 pi by capital N into Rn. So the Fourier series coefficients we multiply both sides by e power minus j 2 pi by n into Rn for applying this interval 0 less than or equal to n less than or equal to n minus 1, and then sum both sides. Okay, we obtain this value. Okay, this also equal to the summation n equal to 0 to n minus 1 1 by n, the summation k equal to 0 to n minus 1 x of k into e power minus j e power j 2 pi by n of k minus r into small n. Okay, so like this, after simplifying this, the summation k equal to 0 to n minus 1 x of k, the summation n is equal to 0 to n minus 1 1 by n e power j 2 pi by n k minus r into n. So like this, we are ready to obtain this Fourier series coefficients. We multiply both with this sum both with side, we obtain this mathematical expression. Now, so the discrete Fourier series pair using this 1 by n with reference to this. Okay, the problem, you will see this particular problem. Okay, so here 1 by n, the summation n equal to small n equal to capital N minus 1 e power j 2 pi by n of k minus r into n. Here 1, k minus r is equal to mn, m as an integer, 0 otherwise. Okay, orthogonally of the complex exponentials. In problematic point of view, you will see, verify that problem, so it is varies. Before that, summation n is equal to 0 to n minus 1 x of n into e power minus j 2 pi by capital N Rn, which is also equal to the summation k equal to 0 to n minus 1 the x of k, where n is equal to 0 to n minus 1 1 by n e power j 2 pi n k minus r into small n. Okay, so it is also equal to x of, so after simplifying this, x of r plus mn, okay, where it is, we can consider this is the periodic x of r. Okay, it is also coming to here, r tends to k, where x of k is equal to the summation n is equal to 0 to n minus 1 x approximation of n into e power j 2 pi by n into what you call k into n. So this is nothing but what you call, right, to verify the number of coefficients. If you are substituting that what you call that n value or k value and capital N value, so that is nothing but a discrete Fourier series. After that, this discrete Fourier series will be appeared where x of n, where it is in terms of this, where x of n is equal to 1 by n, the summation what you call, where k equal to 0 to n minus 1 x of k into what you call the twiddle factor e power j 2 pi, what you call 2 pi by capital N with this, okay, k into n. Like this, right, to verify that the discrete Fourier series. Next, representation of periodic sequence, discrete Fourier series, a periodic sequence. Yeah, if it is the periodic sequence x of n with the period n, where here, where x of n with period is n, where x of n is equal to x of n plus Rn for any integer r. Okay, the discrete Fourier series will be, it looks like what you call that mathematical expression. It is represented as synthesis equation. That is, x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 x of k e power j 2 pi by n into kn. This is our synthesis equation. This equation is based on this equation, somewhat what you call in DFT, or in terms of the DFS with further DFT, we'll try to verify that x of n, okay, or x of k. So where the coefficients x of k is equal to the summation n equal to 0 to n minus 1 x of n e power minus j 2 pi by n kn, where it is analysis equation. So once we are having this all coefficients, or before that there is synthesis equation, by using this all synthesis equation we need to verify that the number of coefficients. The coefficients, after calculating, after measuring this number of coefficients, we will observe that analysis equation is fulfilled or not. Okay. Next, the representation of periodic sequence, the discrete Fourier series x of k, the summation n is equal to 0 to n minus 1 x of n e power j 2 pi by n kn. The sequence x of k is periodic with period. Okay. The sequence x of k is periodic with period n. What do you call x of 0? That means the k value, ready to substitute. If the k equal to 0, x of 0 equal to x of n, x of 1 is equal to x of n plus 1. Okay. Like this, x of k plus n, the summation n is equal to 0 to n minus 1 x of n into e power j 2 pi by n of k plus n into k plus capital N into small n. Okay. Like this, we try to represent the sequence of x of k is periodic with period of capital N is equal to the summation n is equal to 0 to n minus 1 x of n into e power j 2 pi by capital N into k. This is all, we know that this is the twiddle factor, into e power j 2 pi by n, 2 pi n, where we try to verify that x of k, where x of k is, what is that? Discrete Fourier transform. Okay. The discrete Fourier series x of k is equal to summation n is equal to 0 to n minus 1 x of n, that x of n into e power j 2 pi by n 2 pi by kn. Okay. So there is analysis with the mathematical notation. So let the twiddle factor, it is followed by what you call wn. Before this, the weighting function, the twiddle factor wn is equal to e power minus j 2 pi by capital N. Yeah, in analysis equation, x of k is equal to summation n is equal to 0 to capital N minus 1 x of n, the twiddle factor wn kn. Okay. So synthesis equation where x of k, this x of n, x of k is this value, where x of n, this x of n, right, to evaluate that synthesis equation, it is followed by x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 x of k into that twiddle factor, that what do you call, the polarity is changed. So this is the major difference between analysis equation and synthesis equation while we are using that discrete Fourier series, that we will expect that discrete Fourier transform, where x of n applied with the DFS, discrete Fourier series, we will expect that x of k, it is nothing but periodic, like CF continuous Fourier series. If it is discrete, so the discrete like DTFT. The DTFT, discrete Fourier transform, where so we are defining this discrete Fourier transform. The discrete Fourier transform, we are to define discrete Fourier transform. So we are defining the discrete Fourier transform. It is followed by x into e power j omega is equal to the summation where small n is equal to 0 to infinity. Okay. x of n into e power minus j omega. Okay, so here there is a transformation, transforming new what you call new variable. It is called that omega. So here the DTFT, discrete time Fourier transform, discrete time Fourier transform, transforming. There is a transforming what you call n to omega. Okay, the transformed jumped from the n to omega, where small n is in time. Okay, which is time, or in terms of discrete time. Okay, in terms of this omega, where omega is frequency. Okay, transform or jumped from n to small n to that omega by using this particular tool is called as Fourier transform. That's why using this particular tool, this is the powerful tool for evaluating either maybe analytical or synthesis or whatever it is. Using this all analysis, because I'm applying the discrete time signal, so we are calling it as what you call DTFT, discrete time Fourier transform. Now, using this all analysis, right, to verify or what you call the discrete here, the periodic, where discrete periodic or discrete what you call discrete periodic, where x of n is applied to the DFS. Okay, now determine the DFS, discrete Fourier transform of the impulse train. Consider the periodic impulse train is followed by x of n, the summation this particular value. So you have to assign this. Okay, so this problem you will see. Okay, from here we are to verify that DTFT, where DFS, the discrete Fourier series of the impulse train using the previous this one. This is the best example of this. We can consider this is the problem, or maybe example. That example is consider determine the DFS, a discrete Fourier transform of the impulse train. Consider the periodic impulse train is like this. Okay, like where n versus x of n, that n versus x of n. So this is the from this horizon to minus 1, minus 2, minus 3, minus 4, minus n plus 1 to minus n. From here, so 1, 2, 3, 4 and so on up to n minus 1. Here it is n plus 1 or n plus 2 or n plus 3 up to this value. So using this solver, by using this DFS, x of n is equal to the summation n is equal to 0 to n minus 1, delta of n, the Twiddle factor. Here it is the Twiddle factor where n initially that 0. Okay, so it is equal to 1. So here their DFS impulse train, that x of n given to the here where 1 n is equal to Rn, where R is an integer, 0 otherwise, where the time where x of k is equal to this summation n is equal to 0 to n minus 1, because of previously that is n versus x of n. Now that k versus x-axis is the k, where x of k. Okay, so here in this case, here from this origin 0, minus 1, minus 2, minus 3, 4 and 2, minus n plus 1 and minus n. Okay, these are the endpoints from here to here. Okay, from here to here, where x of k is equal to the summation n equal to 0 to n minus 1 into delta of n, the Twiddle factor Wn kn. So initially that kn value is 0 and it is also equal to that 1. Okay, now where x of n is equal to 1 by n, the summation k equal to 0 to here 0 to n minus 1 x of k into that particular brittle factor. Okay, here that x of k dts discrete Fourier transform where the brittle factor is wn kn, but in inverse of IDFT, I inverse discrete Fourier transform, it is followed by x of n is equal to 1 by n, the summation k equal to 0 to n minus 1, x of k, the twiddle factor, here is the polarities are changed, minus x of n because of the inverse of the DFT. Okay, now where that omega, the twiddle factor, where omega wn is equal to e power minus j 2 pi by capital N. Of that we are right to simplify that IDFT x of n, where x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 e power j 2 pi by n into k and n. Okay, so now it is, if it is orthogonality, so right to verify that x of n. Okay, where x of n value, if it is any integer value or is integer value or maybe 1, like this, we right to analyze. Here next one is the discrete Fourier series coefficients. It may be a duality in the discrete Fourier series. If the discrete Fourier series coefficients is the periodic impulse train, determine the signal using this one more example where y of k is equal to the summation r is equal to minus infinity to plus infinity n into delta of k minus r into n. Like this, here n point and y of k, initially that here is 0, 1, 2, 3, 4, 5 up to n. Okay, this side minus 1, minus 2, minus 3, minus 4 up to minus n. Like this, you can represent that n value and y of k. Okay, so it is using this all simple example. So how they are solving this, where x of n is equal to 1 by n, summation k equal to 0 to n minus 1, x of k, the twiddle factor, because of this is your it is nothing but inverse discrete Fourier transform, where x of n is equal to 1 by n, the summation k equal to 0 to n minus 1, x of k, the twiddle factor, because of IDFT, the twiddle factor wn minus kn, go on applying with this, what you call DFS, that x of k, that is nothing but what you call discrete Fourier transform is equal to the summation n is equal to 0 to n minus 1 x of n with the twiddle factor. Okay, like this we are to evaluate of that. So we are to verify that output response y of n is equal to 1 by n, the summation k equal to 0 to n minus 1 y of k into the twiddle factor. Okay, so after that we will expect that all 1 by n summation k equal to 0 to n and k of wn, that twiddle factor is equal to wn. If it is kn, if it is n value is ready to substitute, okay, k value is equal to 0, like this, wn 0 is equal to 1. Okay, so these are the related to the duality in the discrete Fourier series. So in further, now we will define that DFT, discrete Fourier transform, of what do you call in this duality series. Okay, so in this the DTFT, you have to remember that DTFT, discrete time Fourier transform, with the IDFT, inverse discrete time Fourier transform. Now we will define that DFT where input, that input is x of n, but output is in case of DFT, discrete Fourier transform of the x of k, we know this, okay, that is followed by where x of n, apply with the discrete Fourier transform, we will expect this x of k. Just now we have verified all. This is the decouple it by using IDFT. Therefore, that is nothing but where x of n is equal to what you call DFT, okay, or with IDFT, inverse discrete Fourier transform, okay, x of k. So by definition of this, your what you call the DFT, discrete Fourier transform, where x of k is equal to what you call the summation where n is equal to 0 to what you call n minus 1 x of n into e power minus j 2 pi n 2 pi by capital N into n into k. Okay, so where here in this case where n is ready to substitute, where n is equal to 0, 1, 2 and so on, capital N minus 1. Okay, so like this, try to verify after dualities. Now after using this discrete Fourier series of the periodic rectangle pulse train, so it is periodic sequence with period equal to n is equal to 10, okay, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it is given. This is the example. One more example. The periodic sequence with the period is n, 10, capital N is equal to 10. Okay, under this, so what is the desirable formula where x of k is equal to summation n is equal to 0 to what you call the 4 w. How many samples are available here? It is available what you call 4. So 0, 0, 1, 2, 3, 4. So that means how many samples here? It's around what you call 5. That means where capital N is equal to 5, where n minus 1 here it is 5 minus 1. That's why it is mentioned where x of k is equal to the summation small n is equal to 0 to n minus 1 is 4. Okay, the twiddle factor n is 10. As per this, the discrete Fourier series of the periodic rectangle pulse train is periodic sequence with period is n is equal to where since capital N is equal to 10. Okay, m is equal to 10. Here it is also equal to 1 minus that wn 10 because of that k minus 5, n value is 5 and k equal to k. Okay, with this, so w10 is equal to e power minus j 2 pi by 10. Okay, like this, if you are ready to verify, this value into what you call, so it is up here, where this value into, okay, where x of k is equal to e power minus j by k of pi by 10 by e power minus j k pi by 10 into e power j pi k by 5 by 10 by this value minus e power minus j pi k of pi by 10. Okay, like this we write to simplify. Okay, simplify these values, and the magnitude of the DFS, discrete Fourier series, the magnitude is like this with reference to the previous values. So of that try to calculate, we should measure certain values, the magnitude of the DFS and so on. But according to this DFS, discrete Fourier transform, based on this discrete Fourier transform, here we are right to consider that DFS, how it is appeared. So there is a, before that entering that DFS, what do you call, by definition of dt of t, dt of t. So with this definition of dt of t, discrete Fourier transform, where x of omega is equal to, what do you call, the summation where small n is equal to 0 to infinity x of n into e power j omega n. Okay, so here in this case, say consider for the frequency response of the sampling of that omega, you have to consider. So like this, there is a, what do you call, we have to draw this circle, easily can analyze. Okay, now so here it is initially that 0, that omega is moving like this, is continuously on this circle, that omega from 0 to 2 pi, go on moving in this direction, where we try to observe that where r is equal to 1, that radius, that omega we try to verify here. Okay, from here to here the radius, now it's coming counterclockwise direction. Okay, now we try to verify that, what do you call, the frequency response of the sampling of this omega is continuous on this circle from 0 to 2 pi, where in discrete Fourier transform, where in a discrete Fourier transform is frequency sampling of discrete time Fourier transform. Okay, so now let us take by definition of DFT, where this already we have discussed this definition of discrete time Fourier transform, where x of k is equal to what you call the summation small n is equal to 0 to capital N minus 1. Okay, x of n into e power minus j 2 pi what you call 2 pi by capital N into nk or kn. Okay, this is our related to this value. From this is equation 1 and equation 2. With reference to this equation 1 and equation 2, x of n is the difference, where in terms of the twiddle factor, based on the twiddle factor we try to decide. Based on the deciding factor, we will try to verify that where DFT, discrete Fourier transform, there is a efficient computation. If the samples are discrete, or the samples are discretize the frequency domain, so we are going to verify that DTFT. Okay, so the DTFT, with this the DTFT and DFT. So here we are ready to evaluate here the weighting function or maybe twiddle factor, where the twiddle factor W, what you call that omega is, we know that one, 2 2 pi k by small capital N. Okay, how it is appeared this one? With this mathematical notation, the formula of DFS, at omega value, the 2 pi into k by capital N. Okay, with this, we have to analyze. How we are analyzing with this? So, somewhat same circle. The how maybe parts of N, how they are substituting the N value and the K value, and so on. For this, we have to sketch this all. So where 0 here, initially that all what you call like this, from here to here, suppose you have to sketch. So from here to here, we have to sketch this circle. Initially this is the 0. Okay, here it is 1. So here it is 2. Here it is 3, 4, 5, 6. Here that's 7. Okay, from here, so go on using here where initially that pi by 4, here pi by 4. Now it is moving. Next 2 pi, 2 pi by 4, 2 pi by 4. Next 3 pi by 4. Because of we have to substitute these all values that we are ready to evaluate the discrete Fourier transform. How it is varies that a discrete. Here we can jump the circle. You don't move to this circle. How it is moving from 0 to up to 7. Okay. Next value is this is nothing but what you call 3 pi by 4. Next 4 pi by 4. Here 4 pi by 4. Next 5 pi by here 5 pi by 4. Next here it is 6 pi by 4. Next here it is what you call 7 pi by 4. Next last one up to here 8 what you call 8 pi by 4. This is where it is how many parts of N. With this, how many parts of N easily can analyze, where here we have to substitute where k equal to how many 0, 1, 2, 3, 4, 5, 6, 7. So that means the k value is ready to 0, 1, 2, 3, 4, 5, 6, 7. So how many here? It's around 30. It is 0. Next, k is restricted from 0 to here it is. The k value is restricted to 0 to 7 only. Okay. So that means k is restricted from 0 to 7 with the capital N minus 1. Okay. So what is, so how we are deciding what is the N value? N was here it is, N is ready to decide. If k is assigned where capital N is equal to how many samples? 8 samples. So DFT is frequency sampled version of, finally the DFT is frequency sampled version of discrete time Fourier transform, that is the relationship between the discrete Fourier transform versus discrete Fourier transform versus discrete Fourier transform, or discrete time Fourier transform versus discrete what you call Fourier transform. Within this the value. So by using this all, or directly we write to verify that the DTFT are discrete time Fourier transform, discrete Fourier transform, and so on. How it is efficient, we write to deciding the factor. So sometimes we write to calculate this all value. So we know this all. We have to remember this all properties. Property one is linearity. Okay, after already we have discussed this one. The properties of discrete Fourier series is required. Sometimes the shift of the sequence is required. That time we have to remember this all properties, how it is varies, how it is the shifting the Fourier coefficients by an integer 1 l, or the properties, duality property we have to remember, because of that we are all familiar with this all properties previously we have discussed. Okay, with this duality, after that we go for some how it is coming, that all proofing and so on by using this all periodic convolution. So how it is, where is the DFS value or other values. Okay, after that, so right, evaluate that DTS and discrete time Fourier transform or DFS, how it is varies. Okay, directly we are ready to evaluate that the what you call, if it is DFS and DTFS, the efficient competition, whether it is complexity or not. So easily can decide the values. Okay.
Like, share and subscribe. Hit the bell icon for more updates.